Good morning. This is the eve or the period right before my 7th period mod midterm. Hope you guys had a great Martin Luther King Day off. We have two things to talk about. There's like 6-1. There's slope fields. And in slope fields, this is one of those weird, these two sections are one of those weird sections in calculus that maybe you'll see it, maybe you won't, maybe it'll be a part of a question, a free response question or something. But it's really not that bad. If you know derivatives being the slopes of tangent lines, we're going to be all right. So let's look at this slope field. In this slope field, it tells me that the derivative is negative x over y. So at each point, what I'm going to do is I'm going to make a line that represents the slope at that point. For example, let's take 0, 0. 0, 0, it's not even defined, okay? So the slope, like sometimes you'll see the slope look like that, all right, because that's an undefined slope. It's up and down. Let's look at a point like 1, 0. When I plug it into this equation, I get negative 1 over 0. So anything with a y of 0 is going to be undefined. Excuse me. So y equals 0 is going to be all these points right here. So they're all undefined slopes, which are up and down. So that takes care of anything that has 0 here. What about like 0, 1? Well, 0, 1, which is right here, has a slope of, you put in 0, has 0. A slope of 0 looks like that. And that's all we're going to do for all these points. All right? A lot of times it's on a big graph, so you have to look at some of the integer points. Let's look at 1, 1, something a little different. 1, 1, the answer is negative 1. So negative 1 is a slope. How do I show negative 1 slope? I show it like that. Okay? Let's look at 1, 2. 1, 2 looks like it's going to be negative 1/2. So it's kind of doing this. It's getting a little less. All right, I don't know if that's less. You try the best you can. At 1, 3, it's even closer to 0. So it looks like that. Let's look at let's look at 2, 2. 2, 2, it's negative 1. So it's going to be negative 1 at 1, 1, negative 1 at 2, 2. Let's look at 2, 1. All right, so basically I'm going to go through all these points. And I'm going to say 2, 1, well, that's going to be negative 2, so it's a little even more negative. So I draw a steeper negative line, that's all. And at 2, 3, it's going to be even less steeper as negative. And that's what's happening. Let's go on the other side. Let's try like negative 1, 1. Well, that's a slope of 1. Try negative 2, 2, that's a slope of 1. And then try negative 3, 3, a slope of 1. So you're starting to see what's going to happen here. If I go negative 1, 2, that's 1/2. So that's a little bit lesser. And then if I go here, and notice all these, when x is 0, is 0. So what's happening is you're getting this parabola-like slope field. Let's look downstairs here, okay? And basically that's what's happening. You're looking for a pattern. Over here, let's look at like negative 3, 2. Now let's do them all. What the heck? Let's go negative 2, 1. So I'm plugging negative 2. Obviously, the x is changing. So negative 2, 1 is 2. So that's a little bit steeper. It's crazy steep. All right, that's crazy steep. So let's get a little steeper, but not crazy. Okay, something like that maybe. I don't know. And let's look at negative 2, 3. Well, that's 2/3. So that's a little less steep, I guess. 2/3 is like that. I'm trying here, all right? Over here, negative 3. Let's go negative 3, 1. Well, that's 3. So that's a much steeper slope. And then negative 3, 2 is going to be 3/2 or 1.5. So that gets like that. So it kind of looks like this up top. Let's go on the bottom. All right, I'm not listing the points anymore, but you can hear me saying them. Let's go for 1, negative 1. So that's going to be 1, negative 1. If I put in 1 for x, negative 1 for y, that's 1. It looks like that. The other one on this side, 1, negative 2. Well, that'll look like 1/2. And then 1, negative 3 will look like 1/3. So I think you see a circle. Okay, so that's what the slope field will do. Sometimes they'll ask you to fill in the graph. Sometimes they'll ask you to fill in the graph starting with a point, and you'll just go and fill in the circle. Let me finish it up. Over here, it's 2, negative 2, so that's 1. Then we have 3, negative 2. That's 3/2. So 3/2 gets a little bit less. Okay, and this is how we do it. So I'm not going to finish this because I think you know how to do it, but this will turn into your slope field kind of looking like this, looking like a circle, okay? And that's a slope field. So you're getting the slopes at every point in this graph, and it gives you an equation right here. Let's continue. So here's another slope field question. Okay, now dealing with some pi stuff. And it's the derivative is cosine. So if I integrated that, okay, if I integrated that, I should get sine. Okay, we're saving this for later. This is later. Okay, save that for later for a minute. So let's do this. The cosine of 0 is 1, I believe. Okay, there it is. The cosine of pi over 2. Cosine of pi over 2. Pi over 2, that's 0. The cosine of pi, I think, is negative 1. And the cosine of 3 pi over 2 is 0, and the cosine of 2 pi is 1. Okay? Well, if I go up here, if I go, and that'll work on the bottom. If I go pi over 2 comma whatever, excuse me, it's going to look like, how do I say, pi over 2 comma, there's no y involved, but you can see from the slopes and maybe just a little bit knowing about the cosine that the graph kind of looks like that and follows the slopes. The slope up here would be 0. Everywhere here would be 0. Everywhere here would be 0. Okay? Everywhere here would be this. Okay? And that's how it's going to work. Everywhere here would be 1. So you can see that it can become a family of things. A family of graphs there. All right? And likewise on the other side. So that's what happens. Because once it's 1 no matter where it is. Because there's no y involved. So it doesn't matter what the y is. If it's pi comma like 75, then it doesn't matter. It's 1. Because there's no y involved here. In the last problem, there was a y and an x, so you had to be careful. Let's look at this one. Sometimes we're asked to solve that. It's one of the problems. Like they'll give you a slope field problem, then they'll say solve it. So we're going to separate the variables. We're going to put the x on the one side and the y on the other side. And this is actually, this is subtract y. So we get negative y dy dx like this. Integrate both sides. If I integrate them, I get negative y squared over 2 equals x squared over 2. And then I get my circle. Okay? So that's x plus y. The other one that we had before, let me go back real quick, is x over y. So if you wanted x over y, and we wanted to find out the dy dx, we want to find out what's going on, okay, then this would be, ready? Watch this one. Okay, the y would go up, multiply both sides by y, so you get y dy, multiply both sides by dx, or put the dx on this side, not both sides, just put it on that side, and you get x dx. So you're going to get y squared over 2 equals x squared over 2, subtract, you'll get y squared minus x squared equals some constant times 2, or 2 times some constant, and that's where you get some type of hyperbola or something like that. All right. I know in this one we got a circle, but oh, it was negative. My bad. My bad. That's why it didn't work out. negative x over y. We'll make that negative, negative, and now when they get together, it's a circle. Cool. So this is called separation of variables. We did a little bit of it. We're doing a little bit more, and we're going to do a lot more next section. That's slope fields. Now you have a worksheet that I would like you to try with the slope fields. All right. It's a slope field. It's one of those. Remember, I copied it on little crazy paper, so it's going to have slope fields. There's method on it both. So speaking of Euler's method, here's Euler's method. It's a numerical method for solving differential equations. There's error involved because, remember, to get up to this calculus thing, the guy with the sandals and the robes, they had to come up with different methods. So Euler's method says something like this. It says, use Euler, and you notice there's a little error here going on. All right, but they use it, it's very much like Newton's. All right, use Euler's method, or Euler, if you want to, the math police might say it has to be Euler. With increments of delta x of 0.1 to approximate y with the initial value of x equal to 0.2, and when x is 0.2 and initial condition f of 0 equals 3. They usually give you an equation. If they don't, you have to make the equation. You have to find the derivative. Okay, that's what this is. You have to find the derivative. And now I'm going to follow this table. It's not taught like this in the book, but my xy is my initial condition. My initial condition is 0, 3. So it has to be 0, 3. Now dy dx is when I put 0, 3 in here, okay? And when I put 0, 3 in there, I get, I think, I don't know why I have 1 here. It's a little weird. Delta x was 0.1. This, I think I got 0. When I put 0, 3 in here, when x approximate y when x is 0.2, 0 times 3 is 0 over 3. I'm going to put that as 0. I don't know what the heck's going on. All right. So then delta y is equal to dy dx times delta x. Why was that 1? All right, I'm back and I'm trying this. So this is going to be 0. Delta y is 0. So then when I add delta x and x, I'm going to get 0.1. And then my new point for y, delta y, is going to be 3. So now I'm going to try 0.1, 3. Now things are going to start moving and shaking. So now when I put this in, I get 3 divided by 3. I get 0.1 here. It's better. Okay? And then here, delta x is still 0.1. That's the difference in x. All right? But now delta y is going to be this guy times this guy, which is 0.01. So now the new x will now become delta x, and x is 0.2, and the y will become y plus that, 3.01. I have now approximated it when x is 0.2, okay? And it becomes 3.01. Very much like Newton's method. I was a little confused before because I'm an idiot sometimes. But we got it going. Let's do another one. Euler's method is an underestimate when the curve is concave up, and when it's concave down, it's an overestimate. I think that's clear. Okay, you saw my graph here that this is an underestimate when it's concave up. Concave down, it'll be an overestimate. Let's do one more example, and then I'll leave you for your work here. Use Euler's method with increments of 0.1 to approximate the value of y when x is 1.3. So I'm going to start out y equals 2 when x is 1. All right? So now dy dx, I'm going to plug in. There's no y, so that's okay. It's 0. 1 minus 1 is 0. Delta x is 0.1. Delta y is equal to this times that. That's 0. Delta x and x is 1.1, comma 2. So now I'm going to do it for 1.1, comma 2. I don't look at that. And now when I do dy dx, I get 0.1. Nice, nice. Yes, you missed me saying that. And then it's 0.1 here. And now this is going to be 0.1 times 0.1 is 0.01. All right, so now my new point becomes